All right. So welcome to our play posit about Kirchhoff's laws and equivalent resistance. So by the end of this video today, our goals are that we be able to calculate equivalent resistance. And we talked a little bit about that in our mini lab for resistors both in series and in parallel, and then apply Ohm's law and Kirchhoff's laws, again, to analyze the behavior of some complex circuits. So we'll talk about Kirchhoff's laws real quick, remind you of what those are, talk about resistors in series and parallel, and then hopefully come back around real quick to capacitors. So from our little simulation lab, we might remember that in a series circuit, our resistance increased as we added more and more and more loads, as we added more and more resistors, and that bizarrely for a parallel circuit in our lab, it seems to decrease. The more resistors we added, the more branches we added to our circuit, the more total current we got. Similarly, for a series circuit, we found that the potential differences added up, and this was, that kind of similar to that loop law, and that but in a series circuit, current is the same everywhere. So sometimes this is called SVC, series voltage changes. So the voltages are different, but for parallel circuits, they're the same. And it's kind of the mirror images for a series circuit. So series has constant current, and parallel, those branch currents add up by the junction law. So again, the junction law tells us that whatever current I have coming in, let's say I have 5 amps coming in, has to come out. So maybe I end up with 2 amps and 3 amps. Maybe I end up with 1 amp and 4 amps, but I will never, ever, ever end up with 3 amps and 3 amps, because that is a mysterious extra amp coming from somewhere else. So they have to add up perfectly. Similarly, our loop law tells us that for any path that starts and ends at the same point, our total loop voltage is 0. And I just want to be very careful here to remind us that let's say we've got some battery of a voltage E, and let's say we've got 2 resistors, R1 and R2, and we've got some current through our circuit, I, and it's going to be the same everywhere because this is a series circuit, that our loop law we would write as, assuming we're going in the same direction as current, we'd get plus E, the voltage from the battery, minus V equals IR, we'd go IR1 minus IR2 equals 0. That is, we have our battery is increasing our voltage, but our resistors are decreasing it. There's a voltage drop. This is what we refer to sometimes as the voltage drop, because the voltage is dropping. All right. Now, we kind of touched on this a little in the lab, but I wanted to spend some more time on it. There's this idea of equivalent resistance that we'll talk about. There's a lot of interesting questions. And equivalent resistance is basically to say, what if I treated my circuit as a black box? What if I took my whole circuit and I just put a lid on it? And I kind of said, what does it look like? I'm going to apply a certain voltage to it, see how much current comes out, and I'm going to say, what kind of resistance does it look like? And so we're going to kind of define our equivalent resistance this way. It's using Ohm's law, but it's the total voltage applied divided by the total current observed. So what's that relationship look like? So if we look at a series circuit, well, let's try to use our loop law here to analyze this. So here I have 3 things, R1, R2, and R3, and I've got some total current. Well, my loop law tells me that I'm going to have V total minus R1 I total minus R2 I total minus R3 I total equals 0. But of course, this is a series circuit. All of those currents, all the currents are the same at all 3 points. So we can kind of rearrange this, and what we get is V total, I'm going to move some stuff over to the other side, equals I total times R1 plus R2 plus R3. So what we find is for a series circuit, our resistances just add up normally. You just add them up. So if this is, 1 ohm and 2 ohms and 3 ohms, my total is going to be 6 ohms. That would be my equivalent resistance. So here's an example for you to try. What is the equivalent resistance of this circuit? Well, if you said 60 ohms, you're on the right track. It is a series circuit, so we just do 10 ohms plus 20 ohms plus 30 ohms equals 60 ohms. So if your circuit really needed a 60 ohm resistor, but you didn't have any 60 ohm resistors, you just had a 10, a 20, and a 30, you could just connect them all up like so and get a 60 ohm resistor. All right, what about in parallel though? Parallel is a little bit different. Parallel is a little bit different. Instead of using the loop law, I want to apply the junction law here, just because. So I'm going to look at that I total. And I'm going to ask, what is that I total equal to? Well, I happen to know that that I total is going to be equal to, I'm going to have some I1, some, oops, that only goes this way, some I2 here, and some I3 here. So I can go ahead and write by my junction law that this is, of course, I1 plus I2 plus I3. But I happen to know what I1 and I2 and I3 are. I happen to know that I1 is just going to be, well, they all get the same voltage. So this is really just going to be V total divided by R1 plus V total over R2 plus V total over R3. But of course, I total, this black box thing, is just V total over R total. So what we find is this weird relationship, which you might seem familiar to you. 1 over R total, or 1 over Req, our equivalent resistance, is going to be equal to 1 over R1 plus 1 over R2 plus 1 over R3. And so this one actually works out a little bit differently. You add them in inverse, they add inversely, and then you have to reinvert them one more time. So you get this weird result where if this were 1 ohm, 1 ohm, and 1 ohm, I would get 1 over 1 plus 1 over 1 plus 1 over 1. I happen to know that that's equal to 3, but of course I still have to flip it over. So my REQ in this case is not 3, my REQ is 1/3. It actually goes down. All right, so here's an example for you to try. We've got a 15, a 4, and an 8. You'll need your calculator for this. What is REQ? All right, well, let's break this down real quick. We're going to get 1 over R. 1 over REQ is 1 over 15 plus 1 over 4 plus 1 over 8. My calculator tells me that this is equal to 53 over 120, but that is not my final answer because I still have to invert it. My final answer for REQ is in fact the reciprocal of that. Wow, that's terrible. Is in fact the reciprocal of that is 120 over 53, which is about 2.26 ohms. And you might notice that that REQ is smaller. It's smaller than 15, it's smaller than 8, and it's certainly smaller than 4. And you'll actually find this every single time for a parallel circuit or anything that adds inversely. It always gets smaller. So if this were a multiple choice question and your choices were, I'm just going to do 3 choices. Your choices were like 6 ohms, 5 ohms, or 3 ohms, you'd probably guess 3 ohms because it's smaller than any of the inputs. 6 and 5 would be impossible. So in parallel, you'll always end up with a smaller number. So what I'd like you to do now is take a look at this and try to figure out the equivalent resistance here. Just take a minute and try. All right, this one's a little bit interesting. This is what's called a combination circuit. And what we want to do is break it down carefully. And what I'm going to do is I'm going to actually carve off little chunks, kind of like we did with capacitors before. So I'm going to take these two. These are perfectly in parallel. And I'm going to squish them together. And I'm going to say it's R1 and R2. So I'm going to call their combined resistance R12. So 1 over R12 is going to be 1 over 100 plus 1 over 250, which happens to be 7 over 500. But if you solve this out, you get R12 equals 71.43 ohms, which makes sense. It's smaller than either of those. I'm going to do the same thing over here. Smush R3 and R4 together. 1 over 350 plus 1 over 200. And if you solve that out, that gives you an R34 of 127.27 ohms. And then if I want to put it all together, what do I get? I go and I say R1234. Well, these are just in series with each other. They're two parallel chunks in series with each other. So I get to add them up, and I get 198.7 ohms for my final resistance. Excellent. All right, in our last couple minutes, I want to see if we can connect this to if we can connect this to capacitors. So we're actually going to do this in class. If you want to do it, you can look for it. But my question is, what if I want to find all the individual currents? What if I want to find I1? What if I want to find I2? We will do this in class, but it's a really interesting question. What I would suggest is work backwards. Start by finding the total current. And then finding some voltage drops. What's the voltage drop across this whole bit? And then you break it open. We spent all this time smushing things together. What we're going to do is we're going to work backwards. We're going to crack it open bit by bit by bit. I just want to come back really briefly and touch on this point that for capacitors, if I have them in parallel, we kind of claimed that their total charge was given by Q equals CV. And this is, again, similar to the junction law. The charge has to add up. So this is kind of how we arrived at those rules for capacitors, because we happen to know that Q total is like C1 delta V plus C2 delta V plus C3 delta V. But of course, we now know for parallel circuits that those delta V's are all the same. So kind of the mirror image of resistors, capacitors in parallel add normally. And by a similar argument using our loop law, we can figure out if we look at all of our voltages, right? If we look at all of our voltages, and this is going to be Q over C minus Q over C2 minus Q over C3 equals 0. What we can find is that, in fact, our capacitors in series add inversely. All right. Thank you very much.